Hello, Ganesh. Am I audible? Let's wait for 5 minutes more, and then we'll start.
Hello, sir. Good evening.
Hi, it's fine. Just wait for a few minutes, 2-3 minutes, and we'll start. Okay, let's start. We'll see how the other people will be joining at what time. But anyways, so did you have any doubts in last week assignments?
Yes, sir. Actually, so in week 7 there were three questions on similarity measures. Uh,
Just a second. Let me open it.
yes.
Um, yeah.
Yes. So the formulae for all the similarity measures, like in the numerator, it has the neighborhood intersection of the two nodes. So I thought for all the three, the answer will be zero since there's no common neighbor.
Acha, actually, no. The thing we emailed them to fix the answers, but I don't think so. They have fixed it. So I'll call them. Okay, and I'll check if it's able if it's uh, feasible for them to basically change the answers and correspondingly change your scores.
Okay, so but the right answer is like zero. It
Yeah,
should be
it's
for all
zero.
three,
It's
right?
zero for 8, 9, and 10.
Oh,
And question 4 should be placed below this figure. Question 4, yeah, question 4 should be placed below this figure here because it corresponds to this diagram only.
and so one question I had from week 6
Mm-hmm.
where it says what is the modularity if each node belongs to its own cluster. Like we
Which
have n nodes and each of them belong to their own cluster. So then it should be what should be the modularity? I have written one.
it should be
Um,
0, I think. Where's the question?
week 6 question number
Like,
8.
okay, yeah, it should be 0. I discussed this last time. So modularity is computed by something. Just a second, I wrote it. I wrote it somewhere. So if all nodes belong to a single community, okay, in that case, every node is treated as the part of same group, and modularity will reflect how much denser actual connections within the network are as compared to a random network with same degree distribution. Okay, so that this term is there, na? Delta CICJ is there. Hello.
Yes, sir. But the other the question was that if each one belongs to its own node, like not all don't belong to the same community, but
Which
rather
question? Which question? Question 8 is about if all nodes belong to a single community. That was
okay,
that was purity question. Question 3 was saying about that is purity. Let me share my
okay,
screen. Let me share my screen.
right, right.
This one, right?
Yes, yes, right, right.
This is for purity. This is not for modularity. Okay.
Okay, okay, sir. I got it, but because it will be the other way around.
Yeah.
Sorry.
Any other doubt? Ganesh. Hi, Ganesh. Hello.
Hi, hi, sir.
Did you face
Sir,
any?
can you please explain today's week's SAR model, like how the rate of changes are being derived.
Which one? Sorry.
SIR model, sir.
Okay, so cascading stuff. Okay, explain it. I'll explain it. Uh,
Okay.
let's just discuss the doubts first. For the first half an hour, we discuss the doubts, and then next 1.5 hours we can discuss this stuff. So, if you
Okay, sir.
have any doubts, Ashwin, any basic doubt, then we can move to that. What is that thing called? Epidemic model. So I'll explain each and everything. I'll explain the derivations. There are some not derivations per se. There are basic formula. So I'll explain them as well. Any doubts, Ashwin? Any other doubts?
Nothing from me, sir.
Okay. So Ganesh wants to discuss cascade that epidemic model. Do you want to discuss any concept related to SNA? We can discuss that. Hmm? Okay, let's start then. Uh, I'll follow the book. I'll just discuss all the basic models and I'll show you. You can basically create your own model like that. So, what happens is these models are generally created so that we can map out diseases, we can map out not just diseases, we can map out anything, any sort of interaction, social interaction, how it enters a community, how it spreads within a community, and how it dies. So, for example, you can take the example of Instagram Reels nowadays. So, the problem with Instagram Reels is they are there for a certain period of time in your feed, that music, the trend, the dances, and after some time it dies. So, this thing is not usually seen in YouTube. On YouTube, you will always find old trending videos. This is because of two things: the number of people using what is that? Instagram Shorts, Insta Reels, and the number of people using YouTube Shorts. So YouTube Shorts is used by lesser people compared to Instagram Reels, and so the trends are managed by those people. They are created by those people. They spread within the community by those people. And in YouTube, the community is quite sparse, so they are not very much involved in that, and that's why the whole thing slowly it does not behaves in a similar manner like of say Instagram. So that is basically temporal flow of information, temporal flow of any information, and the overall existence of that information within a network or within a collection of networks is usually studied using epidemic models. So, what week was it in Ashwin? Sorry, Ganesh. Hello.
Yes, sir.
Week 7, right?
Yes, sir. Yes, sir.
Okay.
So actually, chap chapter number week 7, sir, and as per week it is week 8.
As per, sorry,
As per chapter given, it is week 7, sir. As per the chapter name given in the week,
week.
and as per the
Got
week
it.
name,
Got it.
it is week 8.
I got it. I got it. Week 8 is anomaly detection. I am not going into that right now. I will discuss that most probably next week. So I'm discussing the whole thing. I won't be just discussing this the issues which you are facing. In that way, what will happen in future if someone wants to go through this lecture, that person can understand the whole gist of this stuff. Okay, is it fine with you? Uh, Hello.
Yes, sir.
Sorry about that. Actually, if I leave in between, this means my internet is breaking. So please don't drop. Okay, just stay. I'll join within a
Okay.
minute or so. Um, just a second. I'm getting a call. This fluctuation is quite common in IIT, so that's why the people who join from IIT, they drop. So other person was also from IIT, I guess. Okay, so yeah, let me explain it on my iPad. Let me join from my iPad. Is my screen visible? iPad screen.
Yes.
Okay.
Yes, sir.
Okay, so just I'll explain the terminology first, and we'll slowly go because I will be using that terminology in between, and it might be confusing because the terminology is confusing. It's not like some words are common, but other words adopter, adaptation, adoption, etc., etc. Are they discussed in the lectures, in weekly lectures? What is adopter? What is adoption?
Yes, sir.
They'll discuss, right? Anyways, I'll discuss it. So let me go first. I'll discuss, say, network effects, cascading, cascade behavior. So prelims of that is, say, you have this node here. This is infected with some information. I'm not using the term disease, etc., etc., because these models can be applied in other cases as well, not just diseases. And this is the whole gist of it. Because if you understand it with respect to diseases, you might not be able to fathom the like the true essence behind them. Okay, so I'll explain in that term only. So if the node is infected or say infused with some information, this node is called as contagion. Okay, Ganesh, hello.
Yes, sir.
Okay, please stay with me. Okay,
Okay, sir.
just what is let me drop an email because people are not joining. Okay, so if this node, if say you have a network here, and sorry, if this node is a part of say this network, so this infection or information spreads. Okay, and this information when it spreads like this, first it will reach to the nearest neighbors. Okay, Ganesh.
Yes, sir.
So okay, so let me tell you one thing. This is a nearest neighbor here. Okay, this is a nearest neighbor, and this is a nearest neighbor. So what do you think at t time step t equals to 1, this neighbor, how is it affected? How is it affected exactly? Is it affected by this node or is it affected by this node?
Actually, the first node, sir. At time if f time t equal to 0, there is a node infected now, sir.
Yeah. So yeah, basically this is usually infected by main node from which the infection spreads. So that is why it is known as contagion, because at a time step that contagion will affect its neighbors, although its own its its own neighbors can be its own neighbors also can be a part of say its own neighbors can also be one hop can have exact say immediate neighbors of that. Okay,
Yes, sir.
so that is the issue with it. uh, Contagion, just a second. Let me focus silent my phone. Okay, so if its neighbors also have immediate neighbors which are same as its immediate neighbors, this thing, then also the immediate neighbors are affected by the original node, not by uh, the node which will be affected at t equals to 1. So this is the power of contagion, and why I'm telling you this, because this makes these nodes susceptible, okay, while this remains infected. So infection always flows from infected to susceptible. This is the thing which I want you to keep in mind, because this is basically the gist of all the models, SIR, SID, SIR, whatever it is. Okay, so this is contagion. Then adoption. Adoption basically means the event of infection. So this whole thing, this thing is known as adoption here. And adopters are the final set of nodes which are infected. So these nodes are adopters here. And cascade is the final tree. Okay, so adoption is not same as cascade. Cascade is the final graph obtained. And okay, why I'm calling it a tree, not why it's not a graph and a tree. See, this node did not affect this node, it was affected by this node. So in a way this infection flows like a tree structure. Then at next step, since this is already infected, it won't go there, it will go there, and or it will go from this node. The basically this is what this is why the probability is needed, or and ultimately it will go to this node. So it follows a tree structure such that there are no back loops, there are no cycles inside it. Okay,
Yes,
so
sir.
in a cascade there are no cycles, and that is determined by probability. Okay, so yeah, this is that. And then we have basically two types of model: decision based models and probabilistic model. So in decision based models we know which person uh, should be affected by the information we have. Okay, Getting it?
Okay, sir.
So,
That's something called payoff.
sorry.
Payoff, right? It depends on payoff method.
Yeah, not yeah. Uh, if you study it in a payoff manner, so it is also, yeah. You can say it is, say, using payoff we determine the decision based systems. But anyways, we will not discuss the decision based spread of information. We will discuss probabilistic. Why probabilistic? Because probabilistic is a thing which is quite common in real world. Just let
Okay,
me
sir.
go. So we'll discuss probabilistic cascades. Okay. So
Okay, sir.
as I told you earlier, cascade is a tree. Okay, cascade is a tree. So I will be modeling cascade as a tree. Let me just first draw tree structure. It's basically an inverted tree. It's not a tree, real tree. It's an inverted tree. Okay. So the person at top is always infected, and each person, so I'm keeping it uniform, so each person meets d new people. So it is like so it's not a binary tree, it's a denary tree type of thing. Each person, so each person, so say this person on meeting infected node has probability of getting infected as q. Okay. Ganesh.
Yes, sir.
Hmm. So we'll discuss some formula first, and if they are not needed, but this is the basic gist of cascade modeling and probabilistic cascade modeling. Then this q probability is very important here because this determines whether you will be infected or not, because sometimes it depends on the replication factor of information or virus as well. Okay.
Yes, sir.
It depends on the replication factor of virus, because if say a virus is not that much infectious, so this probability is not based on sorry, this probability won't affect a human. uh, the probability will be lower, and the chances of that human being affected is very low. So I'll not discuss this probabilistic stuff, and if you want it I can discuss it, but it's very basic. So this cascade is important for epidemic modeling. And the epidemic modeling has two three things. I'll discuss it. So epidemic modeling has beta as birth rate and delta as death rate. Okay. So this beta is the probability of infection, and delta is the delta is the probability of uh, dying. So birth rate is the birth of infection, not of human being, or not the birth of humans or people in the network. It's the birth of infection, and this is the death of infection. Basically it means node is healing. Okay, and this means node is dying. So basically, if you see, this is contradictory because this is the death rate of virus or infection. This is the birth rate of infection, which means the node is dying here, and this means the node is healing. Okay, contradictory terms.
Yes, sir.
So let's discuss this thing, SEIR model. So in S, this is susceptible, as I told you. Okay. E means exposed. So in this case, these nodes are susceptible because in future they will be susceptible to infection because they are a part of network which has an infected node. Okay. Hello.
Yes, sir.
So this node, just sorry, these nodes are susceptible because they are part of network which has an infected node, while this node here, these nodes, these immediate neighbors, they are exposed because they have the probability q of getting infected at time step t equal to 1, while they don't have this probability because they are not direct neighbors. Okay, so that is what the difference between exposed and susceptible is. Then we have infected, we all know what is infected, and then R is recovered. Okay.
Right, sir.
So basically the diagram of this whole stuff, this basic block looks like this. So you are in susceptible stage. Okay, so they have basically changed the definitions to opposite. Exposed means the node is closer, the node is one hop neighbor of that, and susceptible, yeah, I told the same thing, I guess. Yeah, so they are susceptible, they are not exposed, they are exposed with some probability. Correct, correct. I'm right. I was right in that. Susceptible means you are a part of network which has infection. Then it goes to exposed stage because the infection is growing. Then ultimately it is infected with some probability q, and then it recovers. Okay. So this model start of infection here. Then you can basically exit from exposed, exit from infected, exit from recovered. Okay. And you can also go to, say, you can also just, this can also exit from here as well. So susceptible node uh, can, just because you're susceptible doesn't mean you will get infected, so you can also exit from here. If you're exposed, then you also can exit. And these exit conditions I'll explain in just in a second. Let me just basically show you diagram. So there's also a z thing, I don't know what they have written. Z is, okay, so Z is a node which doesn't follow the idea of susceptibility. This correctly gets recovered. No, sorry. Yeah. This is the basic diagram and let me explain it. Okay. Susceptibles who no longer follow the infection. And the recovered, since susceptible is also, say, recovered can also exit, so they can also exit. Anyways, this is the SEIR model, and SEIR model is basically used to tell the exact with the rough estimate of what an infection can do. So in SEIR model, the problem is uh, it's not a problem. Basically, this can be generalized to say some information spread. say Instagram or something, Instagram Reels type of thing. Okay, so you say you have a common cold, you infect your neighbor, then that neighbor further infects another neighbor. So common cold doesn't kill people. Getting it? Common cold generally doesn't kill people, so that infection does not that infection dies with recovery ultimately. Or say you are in a part, you are your neighbor is infected, you are susceptible. Okay, but you get out of that from here because let me reach with this pointer just a second. You get out of that because you are not exposed to that infection and you are not infected, and ultimately after recovery you either exit like this or this. So this path basically tells this cycle is complete. Why this cycle is complete? If you exit from here, you break the network. Okay, you change your neighborhood, you are susceptible, you got infected, you break the network, you exit. You were exposed, like your neighbor was infected and you exit, you break the network. You are infected, you break the network, you exit. Or you recovered, you exit. But if you live in the same network, then there is a possibility that you can become susceptible again. Okay, or you can exit. Or if you're susceptible, then also you can come to this part and exit like this. Okay, so basically the clear definition of Z is very skeptical, like skeptics. Z is basically skeptics and susceptible to no. So this basically on after coming to this stage, after coming to this Z stage, there is a very, like, you cannot come back to this network. Say you took vaccine type of thing, so you are susceptible, you took vaccine, you came to Z state, but you still live in the same network. Okay, and you exit out of it. You can either exit out of it or you can keep on living. So that vaccine prevented you from further infections, or you recovered, you took the vaccine. But during infection, if you took the vaccine, then ultimately you have to recover, then only you can come here. You cannot, if you're exposed to that. So this thing should also have an arrow, because this doesn't mean if you're exposed you cannot come to this side. You cannot get vaccine and prevent yourself. But this was the basic model. And since this model does not have a parameter that can define death, so that is why this model is used for generalized information spread. Okay. Anyways, here's very basic, and then I'll come to SIR model. Okay. SIR model. So SIR model, you are susceptible, then you are infected with some beta birth rate of virus, and that infection dies with delta rate, and then you become recovered. Correct, Ganesh?
Correct, sir.
Correct, na? Okay. So this is very basic, and therefore there are some mathematical equations that determine the rate of infection, etc., etc. So since the rate of infection is beta, rate means this is probability of infection. If it is 1, this means it will infect all nodes. If it is 0, it means it will infect none of the nodes. So that is why the rate of change of infected / susceptible population needs to be measured, because this is a probability that determines if the nodes will be infected or not, but this cannot measure the rate of infection. So that is why we need to compute this rate of infection. Okay. Okay. Hello.
Yes, sir.
Okay, so say the rate of change of susceptible population. I'm writing this as delta, rate of change of susceptible population. So that is basically ds by dt. Over time, how does the susceptible population change? So you are susceptible. You are susceptible to infection, and ultimately it makes you infected. Correct?
Yes, sir.
You cannot exit from this stage because this model does not provide an exit stage to you. Correct? So if you are susceptible, you will be infected with some beta probability. So rate of change means susceptible population will decrease. Correct?
Yes, sir.
Okay. So initially you have 100 nodes which are susceptible. Then 10 nodes become infected. So this reduces the population to 90 susceptible. So this means it will be negative. Correct?
Yes, sir.
Rate of this probability basically beta. Correct?
Alright, sir.
Okay. Into susceptible count into infected count.
Sir, why we are using infected count here, sir?
Sorry?
Like we are discussing about the susceptibility, sir. Then why we are using the infected one?
We are using infected na. We I didn't get your point. Can you make it clear?
Like here we are calculating the only about the susceptibility population as well, like rate of change of
But
susceptibility.
that susceptible population moves to infected one, right?
Yes, sir.
So we need to measure that as well, na?
Okay, sir.
Okay. So if you have booked in, if you go to sections, is it figure 7.21, 7.21, 7.21? Where's 7.21? No, it's not given. This derivation is not given in the book. Prop, uh, it should be given back. Let me just check. Okay, anyways, I'll just explain this equation. Say this is equation 1. And if I just write beta here, why beta is incorrect? Because beta is a probability. That is not rate of change. Rate of change means you need to have some number there. 5 people are getting infected every second. Correct?
Yes, sir.
Okay. Let me explain this equation by an example. Okay. So say you have this tree. This has 3 neighbors. Then this has 3 neighbors again. Each neighbor has 3 neighbors. This is infected with some birth rate of say 0.33. Okay, so 0.33 means out of 3 nodes, it will infect only 1 node, correct?
Yes, sir.
So at time t equals to 1, there is 3 susceptible nodes, 1 infected node, correct?
Right, sir.
So if I write ds by dt, this means 0.33 into susceptible are 3 into 1, so that means 0.99, which is closer to 1 person per time step, correct?
Right, sir.
So that is what I told, that is what exactly I wrote here. Okay,
Okay, sir.
so at time t equals to 2, there are 2 infected nodes. Okay, so there are susceptible nodes are these 3, then these 3, so 6 susceptible nodes, correct? 2 infected nodes, correct?
Right, sir.
So if I write the same thing, ds by dt 0.33 into 6 into 2, which is equals to 12 into 0.33, means 1 by 3 is equals to 4, correct?
Right, sir.
Is it 4? Let me check. 0.33. Twelve into hello.
Hello, sir.
Just stay, okay? This Wi-Fi issues are there in IT. Um,
So, sir.
I will explain it very intuitively. I'm not. That's why I'm not going definition wise. I'm going it, say, example wise. Why these equations are written in this manner. Then I'll explain the rate of change of recovered nodes, the rate of change of infected population, etc., etc. I'll explain all that. Okay. Yeah, I was doing calculation. Wait a second. 12 into 0.33. Sorry, 12 into 0.33. That is equal to 4. Correct. 3.96. Okay. So this means there's a possibility of 4 nodes getting infected at this time step. Correct? Why 4? No, there's no negative marking. Who told you? NPTEL does not allow negative marking. Okay, anyways. Am I doing it wrong? I know, I don't know. Let me check. So, yeah, sorry. I did one thing wrong. So at time step, because this 0.33 does not satisfy this criteria. So at this time only one node should be infected. Okay. So at this time, how many nodes will be infected? So there are 3 susceptible nodes, not 6 in fact, 3 susceptible nodes and 2 infected nodes. So this means 3 into 2, 6, that is equals to, I will tell you why. This is equals to 2. Why 2? So at this stage, just, my feedback is slow. My iPad is screen is changing, alright, or not?
Yes, sir, please.
Just a second, let it load. Okay. Um, at this stage here, okay, there's a possibility of infecting one node, and this stage, this top one here. Why is the feedback slow? Just a second. Just a second, hold on a second, okay? Let me connect Wi-Fi. Is it visible? Ganesh, visible?
Yes, sir.
Okay. So, what I was saying, feedback, yeah, feedback was good. At this time step here, sorry, at time step t equals to 2. Sorry, yeah, at time step t equals to 2, this node can infect one of these two nodes, or this node can infect one of these three nodes. Correct?
Yes, sir.
That is why the answer is 2 here, and that is why the answer was 1 here at time step 1 and 2. So this means this rate changes per time step. If the tree structure, if the tree structure, if tree structure say, if this tree structure is denary, if it is binary type of thing, or say sequential, if it's sequential type of thing, then this rate will remain constant. Okay, correct? Because
Understand.
this rate is does not only depend on this rate does not only depend on beta, it depends on the number of susceptible as well as infected nodes at that time step. This is why the rate is changing. Correct?
Understand, sir.
Okay. Then we have uh, rate of change of recovered nodes. Rate of change of recovered nodes. So see, dr by dt is simply delta times infected nodes. How is it true? This is just an because the rate of change of recovered nodes does not depend upon the rate of change of the number of recovered nodes. Okay, it depends on number of infected nodes. Correct?
Right, sir.
Say there are 50 people, out of that 40 are infected, 10 are recovered. So the rate of change of recovered nodes will not depend on the 10 people who have recovered. It will depend on 10 people who are infected and they are being treated howsoever they are being treated. So this is why it depends on rate of this depends on number of infected people and not on recovered nodes. So rate of change of delta of infected population will be di by dt is simply beta times minus delta times I. Getting it?
Yes, sir.
Why is it like this? This is originally written as delta time. This thing is written as minus times, like this. Okay. So this
Okay,
negative
sir.
sign basically. So I will make a diagram. I will make a diagram type of thing. So say infected nodes delta is like this. Why is the feedback slow again? Just a second. Just a second. Let that plot load. Yeah. So in sorry recovered dr by dt looks something like this. It has a positive slope. It can be a bit like this, even straight, but it won't be in negative. Okay, because the nodes always keep on recovering while this thing susceptible thing changes. Rate of change of susceptible node decreases because we are basically moving from infected people. We are reducing the number of people infected. This people at time these many were susceptible, at time this many were susceptible, at this time this was susceptible. So ds by dt looks like this, while dr by dt looks like this. But how does di by dt look like? Hmm? Can you tell me how does di by dt look like? Slope of di by dt.
Uh, Initially low, and at middle may be high, and after at the end it may be again low, sir.
Something like this.
Yes, sir.
Uh, how do you say yes, sir? It's not visible on my screen. Just a second. Let it load. Let it load. What's happening with feedback? Yeah, something like this thing. this curve.
Yes, sir.
So this means uh, this means I cannot teach like this. Just a second. Just a second. Let me check. So this means this negative sign which we put here changes the value from first the slope. Initially the slope is negative, then the slope becomes, sorry, initially the slope is positive because infections are increasing, correct? Then the
Yes,
slope is
sir.
negative because infections decrease, and it's still not loading on the screen. Okay, let it load. By till that time, let's ask Manjula if she has any doubts. Manjula, do you have any doubts from last week or whatever weeks till now?
No, sir. I am.
Week 7 had some doubts, like I have emailed them, but they're not responding. So, like the last two questions, their answers were incorrect, and we have fixed it. We have emailed them basically, and let me confirm by tomorrow, and I'll communicate on the group. Okay, so see,
Like actually, common neighborhood and jackpot similarity is zero only now, sir.
yeah, it is zero. It
As
is
per,
zero. It is zero.
but the answer is incorrect, right?
That's what we have emailed. That's what we have emailed them. Let me show you. Let me also show you the email. No, 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 I cannot show. I will have to disconnect my iPad. I will show you later on. I will show you. Just a second. Let me check if my email is open on this device. See, you can see this, right?
Yes.
But
Yes, sir.
8, 9 and 10 because question 4 was moved to question 10.
Yeah, yeah. 9 and 10 actually, as per the formula, it is zero only coming.
Yes, yes, it is 0.
But they have given the answer wrongly.
We have emailed them, but let me confirm by tomorrow because it was weekend now, so they didn't reply.
Yeah, yeah.
Okay, so this is the basic of SIR model. Uh, this slope changes over time based on the increase and decrease of infected nodes and recovered nodes. Anyways, so say this is common cold problem. So you are infected, you are recovered, but you again can get infected. Then there is SIS model. Hello, Ganesh.
So,
SIS model. I'll discuss all the models and I'll just so that people don't have any confusion over time. Then there are independent cascade models are there. Cascade prediction. I'll also discuss some other models, and I won't discuss the equations of those, but I'll discuss how you can model any disease by creating any model, and just you have to write equations properly. That's all you have to do. So SIS model is basically you are susceptible to an infection, you get infected with this beta probability and you recover, but you cannot recover, you again become susceptible. So this is like common cold, but the problem with common cold thing is, okay, it's not given here. The example, the common cold you can recover, but there are some diseases, and you will not get infected again for some time. For some time, you will not get infected with common cold, but there's something. Say you have stomach infection, and that is basically not transmittable directly, so you get it from food poisoning or something. So if you have infection today, you can get it tomorrow again after recovery. There won't be a longer span of recovery. So this type of model generally does not exist in real world, but anyways we study it because there might be a scenario you are infected by some strain of common cold virus, then again you are infected by another strain of common cold virus before recovering. So that means either you have low immunity or the virus strain was strong enough to infect you again. Anyways, and this type of structure in real world, in information spread. Information spread. This type of structure clearly shows what type of thing. How can you map it with some social media platform? News channels. News channels infect you with their bias. You don't recover from that bias because it is basically affecting your mental state. Okay, but news channels have now stopped showing you that bias. They started showing you something else, but over time they again start showing you that bias because you did not recover from that bias. You cannot erase that bias from your brain. You already had it. You were susceptible again, and you got infected with that bias again. Okay, so due to political reasons, I won't be giving any example. Let's stick with this thing. You guys can understand what I'm talking about. So equation again, it's quite simple. You can easily see rate of susceptibility is minus beta si plus delta I, while rate of infection is the opposite of it. And I don't need to explain these equations because they are quite similar to the previous one, but they can be easily understood from this flow. When you compute this, the arrow is in opposite direction, so you take negative. This is coming towards you, you take positive. And SI is used because you want to measure both of the things, because susceptibility to infection depends on the number of susceptible nodes, but infection to susceptibility does not depend on number of susceptible nodes. Okay, correct? Am I right?
Yes, sir.
Yeah, so this is the basic. And there's one thing, there is a ratio, there is epidemic threshold. Epidemic threshold. So when beta by delta is greater than some threshold tau, this means disease will not die out. Correct? Am I right? Hello?
Yes, sir.
But when beta by delta is less than tau, disease will die. So this means tau is the epidemic threshold. Although in real world epidemics die out over time, but in ideal scenario an epidemic should keep on existing till it kills everyone in that population area. So that is why this thing is measured. And yeah, this is SIS model, and I don't think so. There's also SIEZ model, but it's basically for rumor spreading. So I can discuss that as well. I'll just start. I won't go into the equation part. I'll just discuss the basics of it because it's quite intuitive. Okay. So S to I, this is basically beta, which means contact rate. S to Z, S to Z is again contact rate B. What is happening? Just a second. Okay. Then there is epsilon towards this arrow. If you want, I can discuss it, but otherwise it's quite intuitive. So if you're susceptible to some information, some false rumor, you can just exit from it, or you can become infected directly, or after infection you again become exposed to it, and after exposure you again become infected to it, because you cannot go from exposure back to susceptibility, because you are now exposed to that information that is not going to die out from your brain. Okay, so you keep on basically moving between this and this. Okay, and you cannot exit because you already have exit information. What is happening? Some guy is playing football. Okay, yeah. So this is SIEZ model, and then there are independent cascade models as well, but those independent cascade models are basic. But anyways, these are 3-4 basic cascade models, but now I'll discuss 2 other type of models which involve death. Say there's COVID. If I draw its SIERD, whatever you can call it, let's just keep on adding the parameters. So you have you have an infected node in a network, so now you are susceptible to that infection. After susceptibility you become exposed. After exposure you become infected. After infection you recover, and in the infection stage you can also die, and after recovery you become susceptible again. Correct?
That's it.
Okay. Or after recovery you can directly become exposed. Correct? So this type of model is called SEIDR model. Why DR? Because death does not loop back. So basically write it in this way so that after R you should come back to this thing, sort of that. Anyways, so then there are possibilities, and if you start writing equations, so after susceptibility you become exposed with some probability alpha. After exposure you become infected with some probability beta. After infection you become recovery with delta, and after infection there is a possibility of death, that is 1 minus delta. Correct? Ganesh?
Correct, sir.
And just a second. Okay, so this means, say there's a 0.9 or say 90% chance of you recovering, but there's a 10% chance you will die. Correct? Hello?
Yes, sir.
So this, although this thing is, I should not write it like this, because this is the rate of death of infection, but death of infection means you have recovered. So if in case infection does not die, then you die. So that is why this death parameter contains this part. Okay. So there was one assignment. I'll discuss that assignment. Wait a second. Uh, that is what very nice assignment here. So the information cascade model which we have studied is very simplified. Correct? Correct?
Yes, sir.
In real life, there will be a lot more parameters. Okay? So this cascade, I'm not discussing with respect to epidemic model, I'm discussing with respect to cascade models. And I'll discuss those parameters as well. Okay? So in real world, an individual basically enjoys access to multitude of information sources. It's not just like say you are in say uh, let me you don't you are not infected to one source at a time. You are basically susceptible or exposed to a lot of information sources. Okay, so for instance, a person just does not listen to people about whether the restaurant is good or bad, or it prefers to ask why that restaurant is good or bad. Okay, so that question of why part comes, and this assignment was discussed in Stanford. Some course was there. Okay, so I got it from there. So that now the to for information to flow from one person to another, the reasoning part has come into picture. That reasoning influences whether the user is susceptible to that information or not. It's just not like I'm saying this food is waste and that person will just get it. Yeah, the food is waste and it will not eat from there. But just a second. Yeah. But camera is okay. But so yeah, that is that. And so the practice. So that is that, and you need reasoning. You need reasoning to basically come up with some rating, some influence. That reasoning basically influences your perspective and you for you to become susceptible. Say, if some Instagram reel flows into your feed and that says this influencer is bad, just it keeps on saying this line. Will it affect you, or you just want to know more about that, and you start searching Google why this influencer is bad? Am I right, Ganesh?
Yes, sir. It's a
Say you saw a reel that was posted by a person that said person is bad, but you did not trust that reel, so you went to Google and you search about that person. You got into the news or Twitter, and then you saw a lot of tweets about that person. So you basically got influenced by two informations coming from two different people at a time, and you got that information inside your brain, and then you came up with some formula to select what part from that information on the web and that information you got from reel. So that is, and then other factor comes the credibility. So you cannot just trust a person's opinion. You have to trust the credibility of that source. So then basically say, for you to become infected, rate of infection, for you to become infected, what was the formula? What was the equation exactly? It was this thing. No, it was, yeah, it was this thing only. So beta si minus delta I. This whole thing is multiplied by some credibility score. That credibility score basically influences whether you pick the information credibilities or not. Okay. So, for example, Mintra. Mintra has started this type of thing where it gives rating to a user. Okay, rating to a user to determine whether this user is dangerous or not. And so after some time, it can ban the account if that rating falls below a certain threshold. So that rating basically tells Mintra whether this user should stay in their shopping network or not. Okay. Anyways, so there was an issue. Also, the second question of this assignment is, although there are a lot of epidemic models have been proposed, a lot of epidemic models have been proposed. I'm writing this here because the person might not hear it out properly. But none of them was successful during COVID 19. During COVID, none of them, almost none of them was successful. Why is it that? Why do you think they have failed? Ganesh, why do you think they have failed? Ganesh?
Due to lack of credibility.
Credibility, COVID, why there's a need of credibility? Like you have to basically measure the rate of infection.
Like it's based on spreading or information you're asking about.
I, I'm going back to that epidemic models. I have this is cascading. What I've discussed here. Uh, this is cascading. Okay, this is not epidemic model. This is epidemic model. Why do you think COVID models have failed? Why do you think SIERD did not basically measure the exact rate of COVID spread? Why do you
Maybe
think?
lack of proper information.
Lack of information, but yeah, lack of information basically made you infected. But we are not living in, say, what do you say, 1920s or 1820s when the plague infected Europe. We all knew COVID was coming. From November 2020, we all knew COVID was coming. Correct? So how come we could not protect ourselves? And how did
Maybe
it? Sorry.
maybe due to lack of vaccine, we couldn't able to protect ourselves.
Lack of vaccine is one reason. That is why this needs to be incorporated in this model. Lack of vaccine. Say like you have lack of vaccine are there, but India developed vaccine by the end of 2021. But COVID went on till 2022 October something. Correct?
Yes, sir.
How did we go from a vaccine to recovery till 2023? Manjula,
Sir, I have to check this actually. I'm
just think
not
of
at.
something like why did COVID spread like this, and why it was just if I show you, say the COVID chart was like this. Initially, this people, then suddenly a sudden jump was observed. Then the rate of recovery was rate of decline infection was this. But in general epidemic model, the rate of infection increases like this. Why did this thing happen? Remember these three terms, Ganesh. These three terms, remember them.
Okay, sir.
I'll explain why and how these three terms basically allowed the COVID model to allowed these epidemic models not to be basically restricted these models to be applied in COVID case. Okay, so these all epidemic models were developed in the year 1900s. This is a very old thing, hundreds of years before like this these models were developed. Just a second. So the problem with that, these models is they did not consider the dynamic evolving graph. Okay, earlier when pandemic used to happen, earlier when pandemic used to happen, there was no advanced mode of transportation. When plague spread, when plague spread in Europe, plague, the only problem with the only reason why plague can be described in SIDR model easily, because the plague was spread in whole Europe, and that Europe at that time was not uh, restricted by borders. Okay, and the mode of transport did not allow the graph to dynamically evolve. Okay, so let me show you an example here. Say, consider this is Europe, this is Asia. Okay, so Europe is basically connected by land. Back in the day, it was EU without borders, etc. etc. So you can just go from here to here. So basically, the people which were in that network, so if this person, say this is connected to this is connected to this is connected to this, if this is connected to this somehow, the whole of Europe, used to move here and there, and this plague lasted 2 years. In 2 years, people roamed a lot. A person staying in Germany used to go to UK for a job. The person staying in UK used to travel to France for tourism purposes. So this graph, over the time, it somehow became sort of fully connected type of thing. Okay, and when a graph is fully connected, these type of models, SIERD models, they are perfect, because the infection has to spread in tree fashion, not fully connect. I will not say it's fully connected. The graph was not disjoint. The connected components, there was one giant connected component. It's not fully connected per se. It was one giant connected component. Okay, so infection has anyway spreads in tree fashion, and when this graph was perfectly connected, then this model was applicable. Okay, but what happened in case of COVID? Let me draw a world map. COVID started in China, then we had India here, US was here, Europe was here, Australia was here, now South America, Africa. Okay, it started in China. That Chinese person, people got infected, they traveled to South America. South Americans traveled to America. Americans traveled to Europe. Europe infected Indian students. Indian students came to India. Chinese people came to India. Okay, Africa basically got infected because of Europe. Then Africa got Africa sent it to India. Indians ultimately went to Australia. Americans went to Australia. Chinese went to Australia. So see, the problem with this thing is there was sudden change, in connectivity. In Europe, the connectivity changed in this fashion. Okay, this person was here, then ultimately it went to some other part of Europe. But in case of plague, in case of COVID, if one Chinese person came from China, then it basically got China from China to India. Say it came to Uttar Pradesh, so it got immediately connected to 40 crore people. Then that person, 5 people from Uttar Pradesh went to USA. say New York, then it connected to 5 lakh people more. Okay, then say we reached to some third most populous country, like this. So the rate of infection, that's why it followed this pattern instead of following this type of thing. Got it?
Yes, sir.
Okay. So this is why these SEIR models failed. And also the reproduction factor. Reproduction factor of COVID was much higher than say this thing, plague. Okay, so that is why also. So reproduction factor is not taken into account. What we are saying is death rate, birth rate, this is based on number of people. Okay, this is based on number of people. We are not looking at the replication factor of virus anywhere. This is why again it failed, because the for plague the replication factor was constant. Somehow the scientists came to know this replication factor was constant, so they did not factor it out in the equations. Okay, that is why it failed. Anyways, so this was about COVID. Okay, and these SIER models are applicable to COVID if you use these factors. So that's this becomes ultimately very complicated, and it's not easy to write this present this model in 4 5 sets of equations. It takes around more than hundreds of equations to model it out. So that's why there is no proper model to map out COVID 19. Any other disease you want to talk about? Say, what shall we discuss? COVID, dengue, dengue, whatever we call it. Dengue still follows this SEIR D model. Okay, because it's very rare. It's very rare that a person with dengue will travel, and also the replication factor of dengue is very small. Sorry, is very small. Reproduction factor is very small. So even if the person with dengue travels, it needs a carrier like mosquito, vector like mosquito, whatever the spelling is. Okay, so it needs that thing, and if the mosquito is not there, it won't spread. So that's why this is small. So birth rate is much lesser than death rate of dengue. That's why it does not become an epidemic. Got it?
Yes, sir.
Any other doubt?
No.
Manjula? Manjula, do you have any doubt? Okay, tell me a disease. Tell me a disease which you think is difficult to map in SEIRD model, and I'll map it. Tell me something. What do you have? Stomach infection, some sort of thing. So in case of say stomach infection, if it's not caused to you by not washing hands, then that's a hygiene problem. That's a personal hygiene problem, and it cannot be mapped. It cannot be mapped using SEIR, which shall not go to D part, because that is not getting caused in case of stomach infection. But if it's caused, say you'll the water is contaminated in your area, then it does not follow SEIRD model at all, because if this source is infected, it won't work like this. So there is a common source that infects people, correct? Correct. It spreads in a star fashion. Even though it's a viral infection or bacterial, spreads in a star fashion. Ganesh, correct?
Yes, sir.
Sorry?
Yes, sir.
Okay.
Yes,
So
sir,
that,
it is.
yeah. So how will you model this type of thing in an epidemic model? Because cholera cholera was caused in mass, uh, say, very huge number of people, and spread like that, but it was caused due to flies or bad food. Okay, so how will you map this thing? So say this, there is some well that is infected in your area, so you don't go to exposed part because the node around is not getting exposed, so you basically directly go to infected. From that infected, you can again go back to susceptible without being proper recovery. Okay, so if you keep on drinking bad water without before recovery, you can again become infected, or you can go to recovery, or you can this person can die. So this type of model is SIRD model. But this graph is important because this arrow basically tells you can again become infected, and this chain of cycle can keep on continuing until the water source is not fixed. Then this cycle will keep on going. This was not in case of COVID, because if you become infected, you will recover, then only you will become infected after some time because you have developed some antibodies. But in case of this cholera type of stuff, you can become infected and you can just, the cycle keeps on repeating. Okay, if you want to write the equation, so in this equation there is no birth rate or death rate type of thing, because this originates from the one source. So death rate, if this source is not cleaned, so this birth, yeah, so in this thing, this birth rate remains constant in the sense zero. This birth rate becomes zero because if one person is infected doesn't mean it all will get infected. This peak of infection can be like this. So I can just say this birth rate is infinite or zero, whatever you like. So di by dt is infinite. Why is it infinite, Ganesh? Ganesh?
Hello.
Yeah, why is it infinite?
TA by dt, sir.
Yeah, di by dt is, why is it infinite?
Actually,
Because the source is same, all people can come to the well, drink the water at once, and they all will become infected, so it will reach from 0 to 100 at time step t equals to 1 only. So this is very close to infinity or very large in case of cholera type of thing. Okay, but
yes, sir.
recovery graph always looks like this, or it can also drop, but it won't drop just like that because people need time to recover. People need time to recover. Okay, it won't drop just like that, even if source is cleaned, then also people will recover like this only. Correct?
Yes, sir.
So yeah, this is in case of cholera. Now take another disease. Give me a name. Give me a name. We have discussed mosquito vector based. We have discussed waterborne. Air pollution. Air pollution works similar in similar fashion like cholera. So waterborne air pollution is there. We have discussed most of that. Like most of the diseases can be covered in this type of stuff in this type of graph. Any other disease which come to your mind?
Skin disease also, I think we covered, na, sir.
Which one?
Like contact diseases.
Contact diseases.
Some skin diseases, like
Skin
if someone
diseases.
having some skin infection.
That is basically SIER model, na. So say
Yes, sir.
say smallpox is there. Smallpox generally comes when you're in contact with that person. Contact means fluid contact or air contact, something like that. So that can be basically mapped into SEIR model itself. It doesn't require any sophisticated model. Smallpox, chickenpox, fever, viral, mass hysteria. Yeah, that is a nice thing. So what is mass hysteria? You know?
Yeah, but I cannot define it in proper way. Like
Mass hysteria is type of imaginary disease, and imaginary disease which is in mind. So at during COVID, people used to say, na, if they started using, they started thinking about COVID, and they developed some sort of throat infection, throat pain, and ultimately they got so worried that their nose also started blocking. So they thought they have COVID, and their symptoms also got quite similar to COVID. So this is what mass hysteria means. So mass hysteria comes into picture because body behaves in a way, in a manner brain wants it to behave. Adrenaline is the best example. If you are in accident, the adrenaline rushes just like this, and you don't feel pain for a few minutes. Okay, so the this means the brain can control the body. Brain can control the body for us. So yeah, this is what adrenaline rush gives. So the brain, say you are in a flight. There was a show, Doctor House, I think. Doctor House. There was an episode in which person was infected with some disease. It was not infected. He was not infected, but it was basically sort of some, not a disease. It was a body problem, body function problem. Say the person suffered something like stroke, and due to that stroke, left hand started shaking. So people thought he was infected with some infectious disease, and just to just to basically throw this idea out of the people mind, Dr. House announced that this is an infectious disease, and your left hand will start shaking, and you will start sweating and die. He said it is bacterial meningitis, and it is infectious, so it should say bacterial meningitis is infectious, okay? So it should follow SEIRD type of thing, correct?
right, sir.
It basically spreads based on touch. If you have, I touch that infected area, and if I have some injury on my body, that bacteria enters my body and my muscles start dying. Okay, so yeah, but in case of mass hysteria, doctor observed that it mass hysteria also followed the same pattern. Mass hysteria also followed SEIRD SEIR SES SEI pattern. So suddenly and slowly, all people started becoming infected. All started becoming infected. Their left hand started shaking. Okay, their left hand started shaking. They started sweating, and when doctor told them that this is mass hysteria, this has nothing to do with disease. So see, rate of infection was like this. Okay, but recovery was like this. They all recovered within a fraction of seconds, something like this. So still it followed SEIR because recovery was possible when doctor told. It was a psychological recovery. Okay, so that's why it is a flat line curve. So this means death rate was very close. It was close to 1, and dr by dt, the recovery slope was almost infinity because of this was 1. Okay,
Yes, sir.
so yeah, this is what this whole stuff is. This mass hysteria is very common when we are influenced by fake news. Fake news of disease. Which part of India are you from, Ganesh?
South, sir.
No, which state specifically?
Andhra.
Andhra. Have you heard about this Moon type of thing? That was quite common in the year 2004, 2005. If you were.
No, sir, I haven't heard it.
So it was a rumor that flying animal comes and it snatches your face, okay, and your face becomes red. It's like there won't be any injury marks, but it becomes red. So it was because of heat waves. People back in the day used to sleep on their roofs, okay, and when they slept on their roofs were hot. And since the roofs were hot, if they slip out of the bed and their face touched the roof, it became red. And one of the persons started the rumor that it is because of this alien, whatever it is. And then this rumor spread so fast all over the north of India, in basically majorly Hindi speaking belt, that this rumor ultimately led to this type of thing explode, this infection. Like a lot of videos of people, a lot of not videos, news started coming that faces of people were burnt. So because the people who were not very rich, not privileged, they used to sleep on roof due to the cold breeze, and it was so they was during sleep they were so psychologically impacted that their face became red. That was due to fear. But then when they woke up and they saw that red face, they thought they have been attacked, and this spread like wildfire. So again, in this case, the infection was like this and recovery was like this because there was no proper source that could tell them why it happened. There was no doctor house that could clear their psychological issues. So that's why recovery was very flat, very slow recovery over the disease, and it took about 6 7 months to get rid of this stuff. People stopped sleeping on their roofs due to that. So it was all psychological. So yeah, basically psychological mass hysteria type of epidemics can also be mapped in a CIR model, and although their alpha betas, beta and deltas might differ a lot, but this does not mean that they cannot be mapped. They can always be mapped because it's all in the brain. The brain thinks the epidemic will spread, and the brain spreads it automatically. Somehow, all brain of humans connect with each other, and they spread it just like that. So yeah, that. This is all about epidemic models. How many pages have we studied? Uh, 8. Nice. Okay, so yeah, that's all about epidemic modeling using these models. I hope you got it, you understood it. Ganesh? Hello,
Yes,
Ganesh.
I got it.
You got it right? We have discussed a
Yes,
lot
sir.
of things today. So, anyways, I think this will be all. You have any other doubts?
Currently, no, sir.
Say, like, can you think of any other disease which is I have discussed almost? Okay, I'm not going into the mental health disease type of things because they are still like this mental. Let me write it so that people can understand it. Mental disorders or mental health diseases, issues, because they are complicated, difficult to diagnose. Also, lack of experts to diagnose, lack of experts. Okay. So, say a person around you is suffering from depression. This doesn't mean you will suffer from depression, but this also doesn't mean that you will not suffer from depression because it is very complicated to map. It is a psychological issue that depends on person by person. So these type of issues still cannot be modeled using a CIR model. Although psychological hysteria type of thing are easily able to be modeled because they spread on rumor type of thing. But if I start a rumor, say if I start a rumor that yeah depression is increasing a lot in the country, okay, this doesn't mean that you will start feeling depressed. You will talk to the other person for 4 5 minutes about it, maybe half an hour. Then you will just get rid of that issue from your mind, and you will continue started to doing your work. So this type of model cannot be applied to mental disorders or mental health issues. Mostly mental disorders are not contagious, first of all, but mental health issues can be, cannot be. We are not sure about that. We cannot tell exactly what happens. Anyways, that's all about diseases which can be mapped. Any other thing which comes to your mind, Ganesh?
No.
Okay, let me think of one more basic disease. Okay, so bone fracture. Okay, no, 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 no. I can't think of anything. So yeah, that's all for today, Ganesh. Any other doubt? Any not just related to this? Any other doubt related to social network analysis, exam, anything like anything abstract you want to discuss? Talk about this course, Ganesh.
Can, can you give me a little intro about next chapter also, like anomaly detection? A
Anomaly
little bit intro.
uh, intro. I will just say what is anomaly detection. I will tell you, and then just watch out videos. If you don't understand anything, we will discuss it next week. I'll just give you a video. So, what is anomaly? Anomaly versus outlier. They are two different things. They are not the same. Okay. Anomaly
Okay, sir.
means which does not follow a distribution. Outlier also means which does not follow a distribution, but the context is different. Okay. An anomaly can be outlier, but outlier cannot be anomaly. Okay. So
Yes, sir.
anomaly the network means you have heard of gray sheep gray sheep problem in recommendation system. Gray sheep problem means generally in recommendation system it is expected that users will follow certain patterns, but there exists a user which deliberately does not want to follow a pattern, therefore it keeps on messing with the search results, his movie choices, and ultimately messes up with the recommendation system. Okay, so that user becomes an anomaly in that system. Ultimately that becomes an outlier, but we cannot just call it outlier because that is an anomaly that is affecting the results of a model which we are trying to train on that. Okay, we cannot consider that user. Outliers generally come from bad data collection techniques. Bad data collection techniques due to sensor issues. But anomaly is legitimate, yet not useful. It can be used for quantitative analysis, qualitative analysis, to understand the properties. Qualitative analysis, we can use it to understand the properties of users, but it cannot be used for pattern mapping. Okay, got it?
Yes, sir.
Anomaly is not due to a mistake, it is just anomaly. Okay, but outlier is generally due to some mistakes in whatever planning we are planning to do. In data collection, there is some calibration issue with sensor, so that is why the outliers are coming like that. Okay,
Yes, sir.
so yeah, that's that. I think that will be all for the day. And if you want to discuss anomaly, just watch the videos first, and then we can discuss it next week in detail. Okay.
Okay, sir.
Okay, chalo then. Thanks a lot. Bye bye.
Bye, sir.